Welcome to lecture number 35 of graph theory. Today we start with a new topic. So, about random graphs. So, for this thing a small amount of probability is knowledge about probability theory is required, but only a little amount of knowledge is enough. But I will not get into so much of it. So, I am assuming that the students are familiar with the required amount of material. So, but still, so just to remind the things, the students who are find it difficult to remember. So, see we have an experiment, so like tossing a coin, then the sample space omega is the set of outcomes. Say it can be the outcomes, outcome 1, outcome 2, like the set of outcomes. So, in our case we are always dealing with discrete probability, and also the number of the sample spaces are finite and discrete. So, therefore, so that we do not have to get into complicated details, we just have to say that there are this set of outcomes. So, if for instance, if I conduct an experiment like tossing a coin, these are the only possible outcomes that can happen, and for instance, this can be the outcome that a head turned up, this can be the outcome that a tail turned up, or if it is the tossing of a dice, it can be the number on the face that turned up, like 1, 2, 3, 4, 5, 6 outcomes there. Now, in a probability space, each outcome is associated with a probability value. Say it is P of O1, we will write a certain value, say P1, so P of O2 is P2, and so on. The idea is when you sum up these probability values over all the outcomes in this sample space, all the possible outcomes, it will turn out to be 1, and the probability values themselves are always in between 0 and 1. These are the things we have to remember. So, there are the set of outcomes, and then each outcome is given a certain probability value which is always between 0 and 1, and then the sum of the values assigned to them is equal to 1, the total probability is equal to 1. And another thing we have to remember, remember we are only talking about the case when the sample space, this omega, is finite and also discrete. So, the now see, now all our examples only such situations will come. So, the student who is not very much comfortable with the probability theory also can understand what is going on. So, and also even if he has not studied the probability theory in a formal course, he can just read up a little bit, maybe the first chapter from a probability theory introductory book, and that would be enough. So, then another thing we need is the idea that any subset of this omega will be considered as an event, right. So, this for instance, if the set of outcomes is O1, O2, say up to say On, some On, then some S subset of omega is called an event, right. So, that is the way we call a subset of the sample space in the probability theory. Now, what will be the probability of this event? Probability of this event, that will be the sum of say this outcomes which constitute that event. This is what the probability of that event, right. This is yeah, right. So, this notion is enough. Now, the only notion we need is the notion of independence. That means, suppose we have two events, say A and B, and then what is the probability that they together happen. That means, probability of the event A intersection B. So, we say that A and B are independent, the two events A and B are independent if probability of A intersection B equal to probability of A into probability of B. So, this is the third notion we need. And an obvious thing that we have to notice is, suppose A and B are two events, and then what can I tell about probability of A union B? So, this is always less than equal to probability of A plus probability of B, right. This also we will be using. Now, but I leave to the student to study a little bit of basic probability theory if he is very uncomfortable with the relevant concepts from probability theory. Now, here for our purpose we are dealing with graphs. So, consider a graph where the vertex set is V. So, let us say V of is equal to n, there are n vertices. Now, so there are n choose 2 pairs here associated with each of these edges. So, associated with each of these pairs we can have an edge or not. So, we will, so suppose edge is an edge, and then we will associate a small probability space for that edge itself. So, we will call omega e to be the set of outcomes, namely 1 e and 0 e. What does it mean? So, it means that 1 e is the outcome which tells us that the edge is selected, edge because we are going to create a finally a graph by selecting some edges and not selecting some edges. So, we are defining a probability space with a given edge where the outcomes are 1 e and 0 e. 1 e denotes that that edge is selected. Or for instance, if we are, it is like thinking that there is a coin associated with an edge, a given edge e, and then when we are tossing that coin, if the head turns up, we will allow that edge be present in the final graph, otherwise we will not allow that. So, that head, the event that the head occurs corresponds to 1 e, the event that tail occurs corresponds to 0 e, and we also have to give the probability values. See, the probability of 1 e, the event 1 e happening is say we say it is the probability, it is a value we are assigning in between 0 and 1, let it be p, fixed value p, and then what will be the probability of 0 e, because the probability assigned for this and this should add up to 1, this should be 1 minus p, typically it is called q. Now, this is very simple probability space which we usually associate the coin tossing, same thing. Now, the probability space that we are interested in is this. So, we have suppose this so this vertex set is V, corresponding to each pair in it we have this, say we can enumerate it as E1, E2, E3, En, and choose 2, right. These are the possible edges. Now, corresponding to each of these I have this corresponding probability space. So, for instance, with Ei I have associated the sample space omega Ei and the corresponding probability values, namely 1 Ei will happen with probability p and 0 Ei will happen with probability 1 minus p. Now, so we will define the GNP, new probability space called GNP. We will define a new probability space called GNP, and it is given the sample space. Its sample space is essentially the Cartesian product of the sample space associated with each of these edges. You know, the sample space corresponding to this edge, the corresponding probability space has two events in it, two outcomes for it, here two outcomes, here two outcomes. So, when I take the Cartesian product of all these small sample spaces, E element of V square, we get the sample space. So, what is this? This is essentially like you know, either in the position of this we will get for E1 we will get a 0 or 1, here also a 0 or 1, 0 or 1. So, we can think that this sample space is essentially is a string of length n choose 2, where at each the ith bit position 1 or 0 correspond to the ith edge, and we are deciding whether that edge should belong or should not belong to the this thing. So, essentially or we can say that it is a mapping from the edge set to 0 E or 1 E. So, 0 or 1 whether it is selected or not, right. So, in other words, if you think it it means that when we have assigned, when we have decided whether 0 should be here or 1 should be here, 0 should be here or 1 should be here. So, we are selecting some edges and deselecting some other edges. Whenever 1 is selected, that means that edge is there in the graph. When 0 is given for that, that means that edge is not there. So, essentially we can interpret this string as a graph itself with the corresponding edges, the edges corresponding to those with 1, right, value 1. So, therefore, the sample space here, this omega, the sample space corresponding to GNP is essentially the strings corresponding to the set of edges. So, n choose 2 possible edges, and then essentially that string can be interpreted as the graph depending on whether each edge is selected or not, right. So, then how do you assign probability values to each of the outcomes in this thing? For instance, if a string is like 0 1 0 0 0 1 0 1 0, right, 1 like that, then we can assign, this means that E1 has not been selected, that means this corresponds to the probability Q. E2 is selected, so this corresponds to probability P. E3 is not selected, so it corresponds to probability Q. So, this is again Q, this is again Q. So, this is P, this is Q, this is P, and so on. So, finally, if you multiply these values, we will get a certain probability value that can be associated as to this particular outcome as its probability value, right. So, this probability distribution is GNP. The reader may want to verify, so the student may want to verify that this is indeed a probability space, in the sense that if you sum up the probability values that we are assigning to each of these events, we will indeed end up with 1. If you sum up them, it will indeed end up with 1. So, it is indeed a probability space, right. So, for instance, you see if you take a particular outcome as I have told, so it corresponds to a certain graph, right. So, the omega, that bit string correspond to a certain graph, depending on whenever 0 comes, that particular edge is not there, whenever it is 1, then that particular edge is there. So, this particular graph, we can ask what is the probability of this graph appearing. So, this probability of this graph appearing corresponds to the probability of that particular bit string in omega, right. So, we say that this G is a random graph and its probability is the corresponding probability. So, it is essentially if you know the number of edges, it is very easy to calculate, because for each of the edges which are present we will be giving p. So, p raised to m into q raised to n choose to minus m will be the probability of a given graph with respect to this probability space, right, G and P. In G and P, this will be the value of the probabilities. So, again to summarize, what the student has to understand is that we have created a probability space G and P. The outcomes in the sample space, the elements of the sample space of G and P is essentially the graphs on n vertices, all possible graphs on n vertices. And the probability for a particular graph, when the outcome is equal to a certain graph, the probability value assigned to it is essentially this much, p raised to m into q raised to n choose to minus m, where p is some fixed number. So, G and P this p, q being 1 minus p, right, and m is the number of edges in that graph. Now, the way we have introduced it is as the product space of many small spaces, because a small probability space was associated with each edge with just two outcomes 0 or 1, which means that that edge is selected or not selected with probability p or 1 minus p. And then we could interpret each graph as the Cartesian product of these set of outcomes, that is edge is selected or not selected over all the edges. That is what we protect. So, the elements of this omega is essentially the Cartesian product of the elements of each of these small things, and therefore, they can all be interpreted as binary strings, but then those binary strings can be mapped to corresponding graph. So, that is why we say that the elements of this omega are essentially the graphs on n vertices and the probabilities are clear. So, this is G and P. The only next concept you want is that, so consider the event with just consider the event with a given edge E being present in the random graph. So, suppose if we select G element of G and P, right, G and P, G element of G and P. So, what is the probability that a given edge E is present in G? This is the question, right. So, how will you find it? So, because if this E is present, right, so this event can be written as AE. So, the present what is the event, the probability of the event, we are interested in the probability of the event that E is present in the graph. Essentially, we see that this is the all those graphs with E as an edge, or all those strings omega such that omega E is equal to 1, right. So, all those functions such that omega of E is equal to 1, if you are taking it as a function from then the edge set to 1 or 0, right. And the probability, now the probability of AE can be calculated as, because this E has to get the value 1, right, the 1 that happens with probability P. All other edges, any other edge if you take, it can be 0 or 1, right. It therefore, that is the probability is 1 there. So, 1 into 1 into 1 like that. So, this probability will be, so before that, so what we should understand is So, this I think we should do it from the understand. So, what does it mean by the probability of AE? That is essentially the sum of the probability values associated with the graphs with that edge present in it. So, now how can you find it out? Suppose this edge is present, and what about the next edge? The next edge in some graphs it is present, in some graphs it is not present, right. So, therefore, we can see that when you sum up over all both the categories, we will get all. So, the 1 for that, because that is a probability 1 is also there, 0 is also so both the events are present, therefore, we can get 1 there, and therefore, this probability will be equal to 1 if you sum up over this thing. So, the student can convince by summing this up, and then we can see that it is this, the probability is indeed PE. And now, the only thing other thing we have to understand is that, because each of the suppose the probability that for a particular edge to be present in the graph is P, and then now suppose there are two edges E1 and E2. So, what is the probability that both of them are present, P E1, E1 is also present, E2 is also present, that correspond to the sum of the probabilities over the all the graphs with containing both E1 and E2 together. So, that can be seen as P into P square. Therefore, probability of A E1 and probability and A E2 is equal to probability of A E1 into probability of A E2. Therefore, these events are independent also. So, the anyway, to summarize, what we are telling is this in this G and P, the calculations become easy because the event that a particular edge is present in the G and P is P, and the probability that a particular event E1 is present, and the event that a particular edge E1 is present, and the event that particular edge E2 is present, they are independent events. So, because their probabilities, the probability that both of them are together present is actually equal to the product of the probabilities that one of E1 is present and the probability that E2 is present. So, therefore, this is what we should keep in mind. These two things make it very easy to do calculations in this probability space. Instead of, we do not have to think about what is each outcomes are graphs, complete graphs, but when you are dealing with it, we can think that we are thinking of each individual edge, and we can manipulate based on that, right. So, these are just background. So, therefore, if as we go on, it will become much easier to understand. Now, the next point is to do some examples. For instance, we can think of this question: what is the probability that the given graph contains an independent, the random graph contains G element of G and P has a set of k independent vertices? What is the probability? How can I calculate? So, the in fact, if I want a good upper bound for it, this is the way we do this. So, G so if we can, out of the n vertices, we can select k vertices. So, what we can ask, we can consider this event that these on these k vertices we have an independent set. So, what is the probability that this is indeed an independent set. Now, the probability that we have an independent set on this given k vertices is essentially correspond to the combined occurrences of simultaneous occurrences of these following events, namely for instance, if these are the k vertices. So, this edge should not be present, this edge should not be present, this edge should not be present, this 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 should not be present. None of them should be present. That means there are k choose 2 edges, none of the k choose 2 edges should be present present. So, let us say this is E1, this is E2 without we are just using these names E3, so E and Ek choose 2. So, the probability that on this set of k vertices we have an independent set correspond to the probability that we have E1 is not present, right. That is, this will correspond to A E1 bar, right, A E1 bar, and E2 is not present, and right E k choose 2 is not present. So, this k choose 2 events together should happen, but then we know that each of these things are independent. So, therefore, we can multiply them together. This is essentially q into q into q into how many times, that is k choose 2 times q raised to k choose 2, right. This is the probability that this is an independent set, right. Now, if you ask can I get an upper bound that there is a k sized independent set in the graph. The independent set can occur in any of the possible k vertex sets. So, there are n choose k such possible vertex sets in any of the k subsets among these n choose k possible subsets. The probability that we have an independent set is q raised to k choose 2. Now, the probability that there exists an independent set in any of them will be at most n choose k into q raised to k choose 2, right. This will be, that is, this is the probability that there is a there exists k vertices forming an independent set. So, why did you say less than equal to rather than summing up? Because, so they are, for instance, in this k selections. So, some of these events may occur. See, it is not that they are all mutually exclusive. In fact, it is possible that when one of them happens, the other may also happen. So, therefore, we can only say that the total is at most n choose k, if as if they were all mutually exclusive. If we had summed up, we would have got this. So, it can be smaller, right. That is the reason why we are taking n choose k into q raised to n by 2. As a similar question, suppose if I asked instead of independent sets, can I find an upper bound that there exists a clique on k vertices in G, how will we find? So, the same method, we will use the same method, namely we can fix a particular k vertices and then ask what is the probability that there is a clique in it. Clearly, the probability is p raised to k choose 2. Why is p raised to k choose 2? Because for that k vertices to form a clique, we need each pair of vertices to be adjacent. There are k choose 2 edges within that k vertices. So, for each of those edges to be present, the probability is p, and all of them to be present together, it is p raised to k choose 2. Now, what is the probability that exists at least one such clique in it? So, the clique may happen in any of the k vertices. So, we can sum up the probabilities on each of the possible k subsets of the G. So, n vertices, there are n choose k possibilities, there are therefore n choose k into p raised to k by 2 will be an upper bound for the probability that there exists a clique of size k in G. So, these are just examples. I just wanted to illustrate some of the way in which we calculate these probabilities in G and P. So, what we have done is we have introduced a probability space called G and P, where we can visualize this G and P as like each edge is selected with probability p and not selected with probability 1 minus p. And so, if that is the situation, we can assess, we can at least get some bounds for the probability of some events which you are interested in. Like we considered couple of events here. One event we considered was what may be a good upper bound for, or what may be an upper bound for the probability that there exists a k sized independent set in the randomly taken graph, right. So, and another thing we considered was there what will be an upper bound for the probability that there exists a k sized clique in the randomly selected graph. So, these calculations were done with some simple observations that for a particular given vertex k to be a clique, then we should have all the edges present. Therefore, since they all should together happen using the independence of these events, that means an edge occurring and another edge occurring is independent events. Therefore, we can multiply the probabilities together. Therefore, p raised to k choose 2 is the probability that a clique occurs in a given k vertex set of k vertices, but then there are such n choose k possibilities. So, we can sum them over all of the subsets, but then it is only an upper bound because some of them may happen together. So, they are not mutually exclusive events. So, this is to illustrate the calculations involved. Now, see how do we make use of this G and P to do some graph theoretic, to solve some graph theoretic questions. So, in probabilistic, when we use probabilistic method, many times we prove certain statements which are completely combinatorial. That means, there is no real probability content in it in the statement of the theorem, but in the proof we will use the probability. So, this is the way. So, it is a very nice example will be explained now. So, we many of you might have heard about the following problem. See this problem, that suppose you go to a party with at least 6 people in the party, and then in this party there is at least 3 people, always we can find 3 people who are either mutual friends or mutually unknown to each other. How do you show this thing? So, this is like when I say when 2 people then either know each other or they are unknown to each other, that is what. So, now we can think of it as a graph. So, if this is the first person and consider other 5 people, right. So, and then out of these 5 people, so he knows some of them. So, if he knows some of them, we can put a an edge, right, otherwise you do not put an edge between them, right. So, this is the graph, right. So, here also we will have some edges and non edges. Now, we will see out of these 5 people. So, we are grouping the 5 people into 2 categories, the friends of this vertex and here the unknown to this person, right. Now, among these 6 people, so 5 people, so at least 3 should come in the same category. So, let us say here in this case he has shown that 3 of them are unknown to him. So, I will mark with red color here, right, 3 are unknown to him. Now, here we see that among these 3, if all of them are known to each other, then see we already got a mutual friends here 3, but on the other hand, if even one of them is unknown to each other, then together with this person we have a 3 mutually unknown person. So, this is the idea, right. Now, we can always ask a more general question here. For suppose we can ask this thing, we have a graph. So, this can be the graph of several people and persons. So, when they know each other we put an edge, if they do not know each other we do not put an edge, say, or we can use a different color to indicate that there is a they do not know each other. So, there is no edge, right, this is possible. So, like that. So, we can think of it in 2 different ways, either it is a graph. So, there are some edges, some edges are not present, or we can think of a complete graph colored with 2 colors, red color and blue color, like that. Whenever there is an edge we have the red color, if there is no edge there is a blue color, like that, right. And now, we can ask, is it possible that there is always a KR or a KR minus KR bar, that means a complete graph on R vertices is present or a independent set of KR on R vertices is present, KR or KR bar. This is with respect to the graph. When we say that we are just taking a graph on n vertices, we are asking, is it possible that always whichever graph you take, irrespective of the graph you take, can I always say that there is a complete graph on R vertices or a independent set on R vertices. So, if you are thinking of this coloring model, then we are asking, can I always say that there is a red clique on R vertices or a blue clique on R vertices. Let us go to the graph type, graph model. So, suppose we have a graph, we are interested to know whether there is always a complete graph on R vertices or a independent set on R vertices. So, the now to get a complete graph on R vertices, so you will think that suppose there should be lot of edges in the, if there are lot of edges in the graph, then there may be a complete graph on R vertices, but it may not be always the case. For instance, if the number of edges are somewhat less, so it may be possible that we do not have any any graph on any complete graph on R vertices in this subgraph, but then will the other extreme come, that means the complete graph on an independent set on R vertices will appear. So, very interestingly, it so happens that this will, as long as the number of vertices is a little large, this will always happen. So, we will quickly look at a proof of this thing, why this will happen. So, here suppose, so So, before that let's define a certain number called the Ramsey number, because this is a interesting subject in graph theory called Ramsey theory. So, this is essentially one of the initial questions in Ramsey theory. Since we do not have much time, we will not get into that topic very seriously, but we will just introduce this basic problem from the Ramsey question, namely this is the one. So, Ramsey theory wants to show that if the number of vertices in a graph is reasonably large, that means if we have a reasonably large number of vertices in the graph, then whichever is the graph you select, you will always find a complete graph on R vertices, and if you do not find a complete graph on R vertices, you will always find an independent set on R vertices. So, either you will get a complete graph on R vertices or an independent set on R vertices. And what is the how big, what when you say the graph has to be reasonably big, how big? So, it should be. So, that number has to depend on R. So, for instance, small numbers it is very easy. For instance, if you ask of R1, the smallest number such that beyond that number, when the number of vertices in that graph is more than R of 1, then there exists an either a complete graph on one vertex and independent vertex one vertices is trivial, because you can take R of 1 as 1 itself. For in fact, in any graph with at least one vertex, you know that there exists either a complete graph of one vertex and independent set or an independent set of one vertex, because both are same only. But if you look at R of 2, when can I say that there exists a complete graph on either a complete graph on two vertices, or there exists a complete graph on two vertices, or there exists a independent set on two vertices? This should true, because if there are two vertices itself, either we have an independent set here, right, or if there is an edge between them, there is already 2. So, we can take it as 2. And now, the next question was R of 3, which was a more serious, slightly more non-trivial, which we considered. When can I say that there exists a triangle, I mean, or an independent set of size 3, which we have seen. If I take 6 vertices or more, you will always be able to find a triangle or an independent set of size 3, 6, right. So, but could it have been 5? For instance, if I had taken a graph on 5 vertices, can I say that there is always a complete graph on 3 vertices or thing? So, if to show that this is not the case, we just have to show one example. For instance, we can take this example, namely this is a pentagon. This graph, this is a 5 vertex graph. Here we do not have a triangle, we do not have any structure like this, right, in this thing, no. But do we have an independent set of size 3 here in this? No, if we take this, then we can take this, and then there is no more independent sets. So, independent set size is maximum 2 only here. So, therefore, in this 5 vertex graph, we neither have a K3 nor have a K3 bar. So, the number we are interested in, when we say R of 3, we are interested in the smallest number such that from that number onwards, if the graph has so many vertices, then it should be always the case that either we have a K3 or a K3 bar, and any number below this should be such that we should be able to find even at least some graph, at least one graph with the property that neither a K3 nor a K3 bar exists in it. So, here that is why R of 3 is 6. For instance, if we have taken 5, then we can find this example where neither K3 or K3 bar is existing. So, for any yeah, so that is true. Now, the question is for general case, what is R of R? R of R, this is the Ramsey number of R. So, Ramsey number of R means, so what is the smallest n of R, we should say n, such that if the number of vertices in the graph is greater than or equal to this number n, that is R of R, there is, it is guaranteed that whichever is the graph you take, as long as the number of vertices is this much, there is either a complete graph on R vertices or an independent set on R vertices. And below that we have, for instance, when you take a graph on R of R minus 1, this guarantee is not there. You can always find one graph, at least one graph, such that we do not have a case KR, we do not have a KR bar, that means an independent set on R vertices. Such that number is the threshold number is called the Ramsey number of R. And so, now we are interested in finding, so for instance, is it always true that we have an upper bound for R of R? So, why do we think that there exists such an integer for every R? So, it does not look very reasonable. Why should it happen? Because, so it is trying to tell us that when the number of vertices is large, we cannot avoid one of the structures, either a complete graph or an independent set on this given number of vertices. That is what, as long as the number of vertices, it is not totally reasonable to think like that, but why should it happen? So, we are giving a quick proof that when the number of vertices is a reasonably large number, it should happen. For instance, if n is greater than equal to 2 to the power 2r minus 3, we will show that this property will automatically come. Why do we think like that? So, for instance, we can take a vertex, we can consider a vertex. So, there are n. So, first from the given graph G, pick up 2 raised to 2 r minus 3 vertices. So, we can discard this is the set of 2 raised to 2 r minus 3 vertices. Now, this be a special vertex. Now, what we will do is we will the remaining 2 raised to 2 r minus 3 minus 1 vertices, we will group into 2 categories, the ones which are adjacent to it, the ones which are non adjacent to it. It is clear that one of the groups should be by 2 seal of this, that means 2 raised to 2 r minus 2 of it. You know, both of them cannot be 2 r minus 2 minus 1, because then if you sum up, you will only get 2 raised to 2 r minus 3 minus 2, which is not true. So, at least one of the groups should be at least 2 raised to 2 r minus 3. So, let us say without loss of generality, this is the group, right. And now, from that bigger group, we can pick up another vertex. So, maybe we can pick up this vertex, and then here again within this group, we can categorize them into 2, like the ones which are adjacent to it and the ones which are non adjacent to it, right. So, now let us say, so there are remaining vertices are essentially 2 raised to 2 r minus 2 minus 1, and in one of the categories we should have at least 2 raised to 2 r minus 3 vertices, right. 2 r here, this is 4 and this is 5, 2 r minus 5 vertices, right. This is 2 r minus 4 and this 2 r minus 5 vertices. So, we are halving it, right. So, then here let us say without loss of generality, the non adjacent set of vertices are bigger this time, and then we can go into that group and we can pick up a new vertex, and then again we can do this procedure till we end up with just 2 raised to 0 is equal to 1 vertices. In how many steps? In 2 or minus 3 steps we will come to just 1 vertex remaining. But these 2 or minus 3 vertices, pivots that you have picked like this, they depending on how they relate to their previous vertex, we can put it into two groups. Sorry, to relate to the vertices which are below this. For instance, we have selected the non-adjacent side or the adjacent side. We can put them in category, say red category or black category, like that, two category here. So, since we have 2 or minus 3 such vertices, it is clear that 2 or r minus 1 of them should be of the same category. When do I say same category? This r, say for instance, r minus 1 of them belong to the first category, namely when we look from that vertex and categorized based on its the remaining vertices based on its neighbors and non neighbors, the neighbors were more, right. Then this r minus 1 vertices are such that they are adjacent to all the vertices below it, right, which are selected later, right. So, if all these r minus 1 vertices are adjacent to each other, that means they form a k r minus 1, and namely the last vertex, the 2 raised to 0 equal to 1, the last vertex will also can also be joined to that. So, we get a k r that way. On the other hand, if it so happens that this r minus vertices belongs to the other type means if each time they were selected, it so happened that from the remaining vertices, when we categorizes it based on its neighbors and non neighbors, the non neighbors were higher, and then we see that each of these vertices are non adjacent to each other, because when one was selected, we picked up the non neighbors of it, and from that only the next vertex was picked, and then from that only from the non neighbors of it only it was picked. So, we get a collection of non adjacent r minus 1 vertices, and this last one can be added to this to form a r independent set of cardinality r. So, it looks like, so we can see that if the number of vertices in the graph is at least 2 raised to 2 r minus 3, we can always find either a complete graph on r vertices or a independent set on r vertices. It's always possible to find a complete graph on r vertices or an independent set on r vertices. So, therefore, we conclude that r of r, the Ramsey number has to be less than equal to 2 raised to 2 r minus 3. Why is it less than equal to 2 raised to 2 r minus 3? That is because it can be, the number can be smaller, because it is possible that the number of vertices such that the minimum number of vertices such that there is a guarantee that either a complete graph on r vertices or an independent set of r vertices occurs is even below this thing, below this 2 raised to 2 r minus 3. But what we can prove now is 2 raised to 2 r minus 3. We know that the as long as 2 raised to 2 r minus 3 number of vertices are there, this is true, but below that we are not sure as of now, but so with more effort we will be able to prove little better. And now that is not our intention, because we just quickly completed describing this proof to convince the reader that there is an upper bound for this thing. That means, it is not that we are talking a question which is just not possible. That means, we were asking of a number n such that if the graph has more than n vertices, then always there is a complete graph or an independent set of r vertices, right. But it indeed exists, that for instance, if the graph is reasonably large, it will always happen. But in this when we are talking about GNP model, the random graphs, So, our intention more is to illustrate the proof technique of probabilistic method, and this is a problem which is very suitable for that. What we are going to do is to show that this R of R is greater than equal to 2 raised to R by 2 also. So, this is an upper bound and this is greater than it. So, this actual value of R of R has to be somewhere in between 2 raised to R by 2 and so strictly greater than, we can say 2 raised to R by 2 and 2 raised to 2 R minus 3. How do we show this thing? This problem seems to be more difficult. This was a constructive one which was more intuitive. In fact, if you had noticed the technique that we had used in solving that puzzle, more or less the same technique was extended here also. But this question, how will I prove this thing? So, if I want to show that R of R is greater than 2 raised to R minus 2, that means if I take a graph on 2 raised to R by 2 vertices, then this guarantee is not there. That means either a KR or a KR bar is present is not there. That means we have to somehow show one graph on 2 raised to R by 2, even one graph is enough, just an example graph on so many vertices such that there is no KR in it, no KR bar in it, neither a complete graph on R vertices nor a independent set of on R vertices is present in that. So, here for proving this thing we will use probabilistic method in the next class. So, thank you.